Hi, today we're going to talk about artificial intelligence that is based on the human brain, how the human brain actually works, and that's how the artificial intelligence works according to the working of the human brain. So, in our human brain, imagine the human brain an intricate web of neurons, over 86 billion of them firing in perfect harmony to govern every thought, action, and emotion. These neurons, like tiny electrical circuits, form connections that allow us to perceive the world around us, solve complex problems, and even experience the profound depth of consciousness itself. Now, what if we told you that the very foundation of this organic intelligence has inspired a breakthrough in artificial intelligence? So, what you would be thinking about this concept? Artificial intelligence, a field known as deep learning, just as the brain neurons communicate with each other through electrical signals and chemical reactions, artificial neural networks are modeled to mimic this biological process. But the artificial version doesn't reside within the brain, it exists within the circuits of a computer. In a human brain, when one neuron fires, it sends a signal to others, creating a network of responses. The strength of these signals depends on the synaptic connections, which can be adjusted or learned over time. This adaptability, known as plasticity, is how we learn from experiences. Likewise, in deep learning, artificial neurons are arranged into layers, each layer processing the data more deeply. The strength of the connections between these artificial neurons, known as the weights, adjust during training, much like synapses strengthen in the brain when we learn something new. So, the journey to creating these intelligent machines began with the fundamental concepts of artificial neural networks, which is very important for us to discuss this important topic of the day: artificial neural networks, inspired by biological neural networks in our own brain. So, the journey to creating these intelligent machines began with the fundamental concepts of artificial neural networks, as I just said, inspired by the biological neural networks in our own brain. So, how it works? The remarkable thing is that learning's neural networks can go beyond basic tasks with vast amounts of data. A deep learning model, like the human brain, can detect patterns, recognize faces, play games, translate languages, and even drive cars. It's like creating an artificial mind that mirrors how we think, learn, and adapt. But deep learning has yet to truly replicate the complexity of the human brain. Our brains are capable of abstract reasoning, emotional intelligence, and creativity, traits that artificial intelligence is still far from mastering. While machines may be good at recognizing patterns, humans have something uniquely special: the ability to make connections and reason in ways AI simply can't, at least not yet. And as scientists continue to unlock secrets of the brain and potential of artificial intelligence, We stand on this phenomenon of new age, one where machines may think, adapt, and learn like us, changing the very fabric of our world forever. So, this is the first video. In next videos, we're going to talk more about the deep learning neural networks. So some of the special animation programs are available that we can talk about, like uh, the one I'm going to show you here. It's like in neural networks, what we do, let's say this is a digit three, it's written, so we have to recognize. Now you and me, we can tell just by looking at it, this is three, but is it possible for the machine to recognize between these three shapes? Because these shapes are they are made up of different pixels in computer vision. Each boxes or each square of various little uh, parts of light and colors. So it's something in that crazy smart visuals that you can see. So that, let's say, 3 multiplied by 6 or 3 multiplied by 7. It's a simple computation that a computer can do. But the thing is how to recognize this shape. If this shape is from 0 to 9, so they are different, but now you can see right here they are, I mean, very well written with a typewriter or computer. But if you look at that shape, it's hard. So the machine learning and the neural networks, they really help us with this. So what we're gonna do is, assuming somebody's having no background for them to understand, it's very important. So my hope is that you come away feeling like the structure itself is motivated. So if you look at these all, you see, so those dots, this is like a structure in your brain. All those nodes, let's say it's something. Look at the cursor. I'm just moving. So if you look at it right here, like this is a node or a neuron. Let's say it's in your brain. Some information is went from here to this one, then from here it goes to another one, then to another one. But again, some information is coming back, and then it's coming this way, this way, this way. So if you see, it's a cluster of various signals, various connections. So that's how we design our neural network. So if you look at this mathematical computation equation, because mostly the common people, they don't really understand, but it's some kind of a connection between various parameters, various features. Let's say if we talk about that, we have to recognize a shape that has different color, like a cat differs from a dog and dog differs from a cat. And if there are millions of different images in the world, and how you recognize different shapes. So like the project in which we are working in NASA, if you go to space and you're looking for some trajectory, some images, celestial objects, so how are you going to define them? So is it a planet or a moon or what? So if you look at here, again, these kind of different threads, they are connected. That's how our brain is connected with so many cells and neurons. So that's how it actually works. So in deep learning, we talk about tensors, and we do the configuration layer by layer, and this is how the machine learning is all about. And if you look at here down, there is like, uh, say for example, there is a path. You have to come from top of a mountain and you have to go to the ground, so you have to find a way. But your human brain can find a way that, okay, this place is like it is water on your way, it's high, there's a grass or some it's very steep or it's not steep, then you decide. That's your brain. But if the computer has to decide, so which way to come from top of let's say a Mount Everest to the ground, and how to find that way, if the computer has to do so, that's how the deep learning of or the neural networks actually works. So now let's see image recognition. We call it convolutional neural networks, CNN. Convolutional neural networks in which various tensors, various layers of the image, they are studied and the filters are provided, and then we do the image recognition. So let's say it's a plain vanilla from with no added frills. Let's say this is in your there is a vanilla ice cream, and it is in your bowl, and it is some places it's like a mountain, and some places it's digged shallow or narrow paths you have, and you have to find the way. So so ask multi-layer perceptron. So we imagine that we talk about modern variables and plenty of complexity for us to wrap our minds. um, that's how it actually works. Uh, but even in this simplest form, it can learn to recognize handwritten digits. Let's say the digit 9 is here. So, which is a pretty cool thing for a computer to be able to do. Um, but it needs a lot of work. So more A than I. It's like more artificial than intelligence, or more intelligence than artificial. That's how we have to talk about. So neural networks, what are the neurons, as I explained you before, and how they are connected. There's a neuron thing that holds a number. Now we're talking about computers. There is some number in it, specifically a number between 0 and 1. It's really not more than uh, 9. It's like somewhere from 0 to 9, but different permutations. For example, the network starts with a bunch of neurons corresponding to, um, let's say, corresponding to this guy. So 28 multiplied by 28, 784. There are so many. If you see each one of these holds a number that represents the grayscale value. Right here, you can see. So this is, let's say, this is some one number, then corresponding pixels ranging from 0 for black pixels up to 1 for white pixels. Um, then you continuously see this thing. This number inside the neuron is called its activation. So we call it activation. And the image you might have in mind here is that each neuron is lit up when its activation is high number. So all of these 784 neurons make up the first layer of our network. Moving on to the next one, 784, 28 multiplied by 28, right? So now, jumping over to the last layer, this has 10 neurons. If you look here, these are lots of number of neurons, 784. So we are actually decreasing the number of neurons. So as it comes down, so here, let's say you have 10 neurons. So each representing one of the digits, right? So it's from 0 to 9. So 9, the activation in these neurons that represents how much the system thinks that a given image corresponds with a given digit. And there's also a couple layers in between called the hidden layers. You see all those connections, they are called hidden layers, which for the time being should just be a giant question mark, for how on earth this process of recognizing digits is going to be handled. So number two, hidden layers. In this network, I chose two hidden layers, each one with 16 neurons. And admittedly, that's kind of an arbitrary choice. To be honest, I chose two layers based on how I want to motivate the structure uh, in just a moment. And 16, uh, well, that was just a nice number to fit on the screen. Why 16? In practice, There is a lot of room for experiment with a specific structure here. The way the network operates, activations is one. There are so many ways it operates. And of course, the heart of the network as an information processing mechanism comes down. So we're going to continue from here our learning process, and I will try my best to move on to how we calculate various neural networks. So it's like more complex here, and let's move on to a little bit more information that then we will move on to the next segment. So I was saying like. If you look at it, 784, to exactly how those activations from one layer bring about activations in the next. See, this is how it works. It meant to be loosely analogous to how in biological networks of neurons, you see this? Yeah, some groups of neurons firing cause certain others to fire. They give signal to the others. Now, the network I'm showing here has already been trained to recognize digits. So this is called the training mode. We train it, we let it do. Once we train it, then the artificial intelligence, just like we train humans, we train the machines to work as we train them to work. It means if you feed in an image, lighting up all 784 neurons of the input layer. So see, like this, according to the brightness of each pixel in the image, lay like this. So 784, that patterns of activations causes some very specific pattern in the next layer. See this yellow, and which causes some pattern in the one after it, which finally gives some pattern in the output layer, and the biggest neuron of that output layer is the network's choice. So, to speak for what digits this image represents, look at this now. How does one layer influence the next? And before jumping into the math for how one layer influences the next, how does training work? And are we giving enough training, enough information to these machines to work as required by us, or how training works? Let's just talk about why is it's even reasonable. Why the layers? To expect a layered structure like this to behave intelligently, see? So let's see why we are talking about the layers. What is the best hope for what those middle layers might be doing? So, well, when you or I recognize digits, we piece together various components. Like just like your brain, when you come up with somebody's telling you something, what do? You do analysis, you recognize, you listen to the person who is saying what is saying regarding what, which topic, then you decide. Let's say if he's saying let's go to market, if you want to or you don't want to, then it means you will have some kind of image in your brain that okay, this person is asking to go to a market, or who's this person, do I know him? So there are so many questions, and your brain answers those questions to yourself. That's how we're going to train the machine. So 9 equals to something plus something. So it's right now you can see, oh, it's very easy. 9 equals to 0 plus 1, it must be 8. It means it's easy. Oh, that's easy, is it? No, it's not. And also 8 has a loop up top, but it's paired with another loop down low. See here. 4 basically breaks down into three specific lines and things like that. See, down there you see 4 and see 9 equals to 0 plus 1, something plus 1, 8 equals to something plus 0, or whatever all these computations are. Now, in a perfect world, we might hope that each neuron in a second to last layer corresponds with one of these, that anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there is something specific neurons whose activation is going to be close. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. We're talking about upper loop neuron, maybe, right? So the hope, uh, let's see what's going to happen. That way, going from the third layer to the last one just requires what? See, learning which combination of subcomponents corresponds to which digit. Of course, that just kicks the problem down the road. Okay, but recognizing loops is just a hard. It's very hard. And I still haven't even talked about how one layer influences the next. But run with me on this one for a moment. Recognizing a loop can also break it down into subproblems. One reasonable way to do this would be to recognize the various little edges that make it up. Similarly, a long line like the kind you might see in the digits 1 or 4 or 7. See? 1, 4, and 7. So it's hard to recognize, to identify. So maybe our hope is that each neuron in the second layer of um, the network corresponds with the various relevant little edges. So the little edge layer you can see here, we're still talking about 784 layers. Maybe when an image like this one comes in, it lights up all all of the next ones, right? So let's see what happens. See, that's 9 neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop. And a long vertical line, and those light up the neurons associated with a 9. Whether or not this is what our final network actually does is another question. Does the network actually do this? One that will I will come back to once we see how to train the network. We will get back to this. Does the network actually do this? So now I'm going to show you some very complicated kind of coding that I hope you won't be able to understand it now, if being a layperson and somebody who's new to all this. But here I'm going to show you some, you see it's uh, in Pytorch, in Python, in Anaconda environment and Jupyter notebook. This is the code I prepared. So I wrote all that course, and now it's for the professionals, for those who really understand deep learning, the researchers, the scientists, the professors, and the graduate PhD students. They can understand, or the programmers, the computer operators, they know the programming, But the concept I'm talking about is about the deep learning, how we talk about, what we talk about mini badges, forward pass, backward pass, mini badges, convolutional networks, images, and how we decide the gradient descent, the loss, entropy, um, evaluation. So there are so many things. So now from there, this is going to be for the professionals. So let's move on to this coding thing right here. This is the code I just designed today. So what we do is, first of all, the task is that there is an image, like for example, we are talking about some NASA's collection in aeronautics in space somewhere. So there's so many celestial objects and satellites there in the space, and we have to recognize, detect it. So how are we going to do this? This is one of the example. So first of all, import torch. So the torch is given in the in the Python. So that would be NN, torch NN, neural network as NN. Import torch optimize. This is optimizer as optimizer because eventually we have to optimize it. Then from torch vision, import datasets because we need the dataset. So that dataset we will see, we will get from PIL import image. That's the library of the Python. So import NumPy as NP because NumPy is we need it for the mathematical calculations, and from PIL import image. Import this debugger because we have to import that. I did it in the Jupyter notebook in Anaconda environment. I did it in the PyCharm as well, some of the files, and there are checkpoints, gradients there, evaluation and everything is there. Then we have to import matplot library because we have to plot it, our results, right? So matplot use aggregate. So in the beginning we will do some aggregation. So from matplot import pyplot as plot, right? So those who know the coding, they are understanding. So from the from the pill, we will import the image, whatever is randomly it's going to select it. And this is also important that we have the debugger with us. So we will import randomly because we don't know what we are actually getting from the collective data, the collection data that they have. Then import matplot library. So we have to have that because eventually we have to do a plot. This is what I explained just now. So from the torch utilities, data import database because we have to get the data from the database, and then the data loader to give it to the data loader from torch vision import transforms. So we will see later on why we have to get this transforms because eventually at the in the middle or end of the coding, you will see what the transforms are and why we use. So let's say here transform image into tensors because we cannot just do because for us an image is a matrix or a tensor of various multi-dimensional 2D or 3D images, multi-dimensional directions. So we need to have the tensor that it has to be in the shape of a tensor. Okay, so transform compose transforms to tensors. This is what I just said, and then normalize this. So this is point 0.5 and point 0.5. These are our they are at our graph or our x and y components. Or in some cases we have the z component where we talk about the channel as well. So this is our simple tensor because this is just a basic coding. So I'm just we have a simple tensor here. So load database with transformations. So what we're going to do is, do we have the data set? So data set, this is a library, this is a standard of the Python, where it's a big library, it's a collection, some kind of standard. The root divided by data, train true. So if we will get the data and we have to train, if we are getting data and our results eventually would be true, then we're going to download. If we are getting the right image, or if it is an image, because we're working on the image, or because it's a convolutional neural network. So when we talk about convolutional neural network, we talk more about images and computer vision. So transforms, right? So I mean, continuously transform whatever the images randomly you're collecting, transform it from the image to the tensors. So train loader. So because our purpose is for the future work, we have to train the loader. We have to train the loader, the data loader. So what we will have, the data set, the batch size, and the shuffle. So I will tell you what this is. Data sets set will be having so many things in it. So uh, give some batch size. Batch size in the neural networks we also call the mini batch or the badging. So the batch, the purpose is we do the sampling, we decide what size it has to be. So right now I have this 64 size, and we do the shuffling because the data is shuffled from one batch to another or at different positions. It changes. If the shuffling is okay, it means okay, we can go ahead. We do. So why do we do it? Because this gives us more chances, more flexibility to rotate the data or to shuffle the data from one position to another in different mini badges or different samples so that we can have less loss in our calculations. To get a batch, so now I'm telling you this, giving this an image, a command to get the image and label it. So let's say there is a image, so we have to label it next. In next iteration, train loader. So now the loader should know that every time it has to get the image, and the loader has to be trained for its print batch shape. Because now what we are actually looking for, one is the batch shape, another is the image, and the shape size actually, right? So here, 28 by 28 is the position. I mean, or the size, or the this is a part of a tensor. So right now, my batch is like 64 as we have it here. If you look at here, right here. So the batch is here is 64, and one is like the image that we selected, and this is the shape, 28 by 28, 28 pixels by 28 pixels. So the batch shape torch size, now my torch size would be 64, 1, 28, and 28. So it means I will be having this many batches, and for one particular because right now we selected one, and this would be the x and y axis coordinates, right? So import randoms, and we will be doing importing in randomly, import numpy as np, because we need that. That's a Python attribute that is numpy as np. So from torch vision import datasets. Now first we imported dataset from the if you look at here, dataset from MNIST, from the library. Now what we are doing is we are right here, we are looking for the, where is that? Like right here. So torch vision is again an ability, a capability of the Python where it has a torch that looks into, just like the concept is like you have a torch in your hand that does the analysis. So if you have that kind of a torch, you can easily understand that. So from torch vision import data sets, because the torch vision will also be having the data set with which we have to compare the data set that we got from the MNIST, right? So the batch shape torch size right here is right now we got the torch vision import data sets class simple batcher. What we have to do, we do the batching. We have to make samples. So just make some simple batcher, a simple loader that shuffles data. So we need not a very complicated loader, just a simple loader that shuffles the data from one place to another one piece of data to another place, another place moves to another place, and like this, and retrieves badges. And it's not just doing the shuffling; it is retrieving the badges, like getting it back. This is provided to me in this case in the project, since the data input pipeline is not the focus of the part. If it's the focus of the part, then we will work on it. But I did it. I mean, at the end, you will see the coding I did. So it took me many hours to do this, but it's still not final. So still working on the last part of it. So let's move on to the coding again. Okay. So we were here. So now we have to define and initialize self. When we say self, it means that the system, the Python, it has to keep doing it. Uh, keep doing what? Data set and batch size, like getting the data set and doing the batch sizing. And self data set. And once this is done, this is the then it is called a data set. Like then go for another one, right? So this is like a we continuously doing it in a loop. Self batch size. So what we did so far, we did the data set only. Now self batch size is the batch size. So we will do the batch sizing as well. So first we did the we got the data and we told it to keep doing it, and then the batch size, we asked it to do the batch sizing as well, keep doing it, and then do the next, then do the next. Then self initialize shuffling. You start doing the shuffling as well. Shuffle the data initially. So do will we be doing the shuffling again and again? Yes, but there has to be some point where we have to stop the shuffling and then redo it from another point. We will discuss that as well, the position. So now define initialize now initialize shuffling. This is self because we just started here. Look at here, we started. Now it's going to be shuffling. So this generates a shuffled order of data indices. So it will have one index, two index, three index columns and rows and all matrices and everything. So it will be organizing it in indices, resets the index for that shuffled list. So it resets every time. Okay, it reshuffles, it shuffles, then reshuffles, and resets, right? So all the indices and the indexes. So self shuffle in index equals to list range length self data set. So it means there is a one index, let's say number one, that has been shuffled. Then we have to do more in a range. This has to be in a range. So what that range would be, if you go up, see, it's a 64. It has to be somewhere here, right? So because this is what my batch size is, right? So this is the size, so it has to be within that 64, right? So where were we? Okay, right here. So random shuffles, shuffles, indexes, shuffles, indices. So again, it will pick randomly. There's no choice. I mean, the system itself choose picks it up. Shuffle, self shuffle, indices. Excuse me. And self current position 0, because it has to do from the very beginning, from the 0. But that is the reset position. That if you do the shuffling, come back to 0 and redo it, because if you will be shuffling whatever has been shuffled before, it means you're doing reshuffling. So once a data set has been shuffled, so now go to another with a new position, and imagine your new position is 0. Now define and get next position. As I just said, for the shuffler to shuffle, it has to go from one position to another position. Retrieves the next index from the shuffled list. If end is reached, then reshuffle. Okay, so it's not just the shuffling, but it has to retrieve from one index and then move on to the another index in the list, in the shuffled list, because this has already been shuffle. So after shuffling, we have to do retrieval. So if the end is reached, if it's done, it's within that batch, done, then reshuffle again. Position is equals to self shuffle index self current position. So for the shuffler for my machine to be trained, that is like self shuffle. They keep doing the shuffling, all the indexing self current, and then for the next, it's the current position is the next. Then the current position is the next. So self current position equals is plus minus one. So it's all gonna be doing on both sides. If self current position is greater or equal to len self data set. So what was my data set? 64, right? Or depending upon see my right here. Let me go up a little bit more. Okay, right here. See the data set here, the trained data set batch size is what? 64. So it has to do it within that range. Sometime it can be more than that, 128, 256, whatever. So in this example, we are just doing with the 64. So we did this, okay, the position, right? So then the badge gather multiple images and labels as integers. So remember, we are doing it with the integers into a batch for training. So we have to do this in the shape of a badge in the training. Let me just reduce the size of my picture so that you can read the code. Okay, now let's move on to this one. So, gather multiple images and labels as integers into a batch for training. MNIST images are single channel 28 by 28 unit 8 images. So see, this is the size, or you can say the different coordinates, 28 by 28. So that would be somewhere 784. That would be the total one, right? So this data loader flattens each image into 784 dimensions. It means if we have number of images, we are just talking about one for now. For one, that will be 784 dimensions vector and converts it to float 32. So, uh, just like we do the matrix transpose where column becomes row becomes column. So that concept is here. So we flatten it into 784 dimensional vector. So it is a vector that and converts it to a float of 32. So n batch size, because we have number of sizes, we have any number of sizes, return image shape, and 784 data type float 32. When we say float, you understand in decimals, right? So return image shape is number of whatever size, and each of the return, let's say n is 1, then 784, n is 2, 784, whatever. Return label shape n 1, because we have to start from 1, and data type integer 32. That's a float one, right? Okay. So the batch size, self batch size, uh, right now we will do the out uh, images and out labels. What we are getting actually from the batch size, we are getting the images, whatever the output and the output of the labels. Batch size is self batch. Now we just we told it to just keep doing it, so it's doing it. So for in range batch size, that which is within that, what within that 784, and the um, number of the data sets. So if the data sets 1, 2, 3, 4, and every time it's 784, so it has to be in that set. For example, uh, self data set, self get next position. So if it is doing whenever I say self, it means I'm telling it to keep doing, right? Self data set means self get, just to know you go and get it, and then go to the next position, right? So in NP, now as we talk about NumPy, right? As array, example starts from the 0, then reshape -1, then flatten the image, right? So from the 0 and -1, flatten the image, label equals example 1, out image, append as image IM for the image, and out label 1, append as label. So whenever I have the label 1, for example, just do it with the label 1. So this is my reshape right here, and flatten the image because I need to flatten it to continue my work. So out image equals to NP stack, because we will have a stack of output of the images at, and the axis would be 0, starting from the 0, as type would be uh, uh, numpy, right? A number that would be a float, and convert to float 32. So you got the point. So it will be a stack of what right now we're talking about the images. We are not talking about the labels. So if you have the number of images, so images output, you put it on the axis 0, and the type is float 32, convert to float 32. So you will get the images in the form of a float 32. So out for now we're talking about the out labels. Now again, here we had the NP stack, but here we have an NP array. So that was a stack, and now we have an array of various Latin matrices. So out label, and the data type is NP, and we had the data type NP here as well. See, the type was here, that was NP. Here we have NP. So integer 32. Here what we had here, float 32. So why we are having the float with the images, and with the labels we have the integer? Because the labels you can have the integers, but in the images it has to be a float one. So reshape. So what we why we have this -1 and 1, and we convert it to the integer. So the -1 and 1 is because this is the reshape that it can be on the both sides, right? And the number 1. So the convert to integer 32. So return will be my output for the image and for the label. So class layer, we have to define the class, base class for all the layers we will define. So define initialization self, like it has to initialize when it's doing a process, I have to come back to it again. Setup layer parameters and gradients. As in the beginning, I spoke about the gradient descent, that when we are coming from top of a hill, we go down and we go slowly, 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 and gradually. So that's how the word gradient is used. And there are so many parameters we have to take care of. So if we make sure we set up some layer and parameters for our slow step gradients, so if it is fine, we have initialized self pass, it's pass, it's okay, then we go ahead. Now define now is the thing is like we are doing a computation in a forward. Look at the way I'm moving the cursor, like this way, left to right, right? When we will doing a back prop, we will do go back. So in the first computation, in the forward pass, we do the calculations, we calculate the derivatives of one with respect to other, or some calculations, addition, multiplication, and we keep doing it in this direction. See the direction in this direction. And then to reduce the loss, we do a back prop, because the system, the Python knows its back prop, and it understands, it remembers the layers it has moved forward. So now for forward self, like it has to be an automatic X. Excuse me. That's some kind of a variable. So compute forward pass and return output along with context for back propagation. As I just said, this would be a forward pass, and the return, the output of this would be given for the back propagation. So in neural networks, we studied about the back propagation, and we will talk about linear and non-linear computation. And we will see later on, we will do the linear calculations and non-linear as well. So with the linear, we will talk about ReLU. right? Rectified linear unit. So you talk about it. So now, for forward computation, raised not implemented error. So uh, if because sometimes the errors are also implemented, if the errors is not implemented, because when we are implementing something good, something bad is also being implemented. So raise not implemented error. So we should know, okay, this error has not yet been implemented. So define backward. So now what would be my strategy to move back? See, if you look at here, for the forward, we were doing self for some x, and now also we are doing it self, like automatic, right? CTX output gradient. So now I will be having some function of x that would be an output of the forward one, because the forward one was coming up with some function and as an output, so we have that output, and that output gradient we will do the back prop gradually. Excuse me. Computes gradients for input tensor and parameters using the stored context. So what it does, actually, it's very late in the night. I'm just doing it because I have to do it for my project. So I thought, why not to just share with the viewers, for all of you, because I was already, it's like 3 in the morning, like 3 in the night, as we say in back home. So 3 in the morning, and because I have to prepare it for tomorrow. So somehow I was up, so I thought, why not to share with the viewers? Okay, now backward is like output, and the it would be a gradient gradual. Okay, computes gradients for input tensor and parameters using the stored context. So what is the stored context here? Because this was what stored context was with the output of the forward pass, right? So computes gradients for input tensor. So now the input tensor for the forward was this way, and for the backward would be this way, way back, right? So raise non-implemented error as we did before. Okay. So define zero gradients. So some of the gradients are zero. So it means, excuse me. So it means some of the gradients are zero. When we say some of the gradients are zero, means that uh, we don't have to worry about it, or there is no move. So we will define that, right? Sets all gradients to zero, does nothing if the layer has no parameters. Let's say there is a layer which is empty and there is no parameters in it. So what we do is sometimes there are some other concepts like max pooling, average pooling. We calculate with the average pooling or max pooling, and we see if there are no enough parameters, and we do some kind of a diagonal calculation and we make it zero. So if there is something like this, set all the gradients to zero. And if that is fine, pass, go ahead. Then SGD step self error takes a step of SGD using stored gradients descent does nothing if the layer has no parameters. So first we did was the zero gradients, then we did the with the stored gradients, because there were some stored gradients already there. So take a step of SGD using stored gradients does nothing if the layer has no parameters. So now it is doing for the both, for the for the layers which has no parameters, don't do anything, and for the stored gradients, if there are no parameters, leave it. Then define forward self x. See, I'm just doing it again here. It's a repetition of work. Maybe it's I have to edit this. See, this is all repetition. So because as I said, I just wrote that, but it has nothing to do with it. It doesn't. It's not going to affect our code. Okay, now class linear layer. So we as I just spoke to you about linear and non-linear computation. So this is how it is, linear and non-linear computation. So let me just move to this. Okay. So the class linear layer define initialize self in size and out size, because when you once you do we do make a, let's say there is a layer which is linear, it's easy for the computation, it's not exponential, it's not non-linear, so it's easy. So we initialize, put it in an automatic, and in size and out size, so we should know what is its in size and out size, like that the layer. So I will tell you later on what is inside and outside. So from the, so right now you can see three things. One is the self, inside and outside. Initializes the linear layer with weight and biases. It means that if there is a layer and we need to have some weights and biases, because sometimes we need some weight to put with the layers for the calculation purpose, just to make computation easily, and eventually then we adjust the weights accordingly. So initializes weights with uniform distribution, 1 upon square in size, 1 upon square in size. So square root, not square, 1 upon square root in size and 1 upon square root outside. So if you have a matrices or calculation, this is 1 upon the square root of the inside and the outside. So self weights equals to NP, that's our numpy. So the self weights, so it is now again we are putting the weights on automatic. So it's asking it to do it, keep doing it, right? So whenever I say self, it means keep doing it repeatedly, right? Self weights equals to NP random uniforms 1 upon NP square root in size and 1 upon NP square root in size and outside, right? So what we actually we're doing, we are doing a calculation, a class of the linear. If it sees some of the weights and some biases, if they are linear, like there is no exponential and non-linear linearity in it, so it will detect it and will do this computation. So initialize biases to zero. So initially we will have a zero bias, self biases again automatic, and the zeros, that 1 and NP0, 1 and outside. So this will be our biases from 0 and onward, it will move on. So store gradients for weights and biases. Because as I said before, that there was SGD here, stored gradients. So using the stored gradients, so we did this was with the uh, self components, right? So here we have now moving on to this we are done. Okay, store gradients for weights and biases. Self defined weights NP zeros like self weights, and self defined biases NP zeros like self and biases. So automatically it will keep giving the weights and uh, starting from the zero, and as the weights comes, and same is see this the same command, the same is here for the biases. So because it has to give the weights and biases, keep doing it for the in this way it's going to store gradients for the weights and biases, because it has to have some gradients for both weights and biases to carry on the function. So now forward self x, as I said before, and then backward self ctx output here. So save the inputs for the back pass, that is here, because the forward pass is giving us some output which eventually has to go as an input for the backward. So the output of the forward is going to go back to the back propagation. So in linear transformation, output equals to x times weights plus biases. So in the linear transformation, because we are talking about linear so far, right? So the output of what? Output of this, the forward, is the x, that the input that was given to the forward function, with some weights and biases. So where we got the weights and biases? See, we did this. So we have the weights, that's stored gradients, weights and biases. So now this is having three components. One is the input, then the weights and the biases. So what would be input? My data set, image, and the labels. So output is np dot x self weights plus self biases. So output for the linear transformation, because this was given in the forward, so will be uh, dot x, like x is the input, some function of with self weights, because now we did this the weights self and plus self biases. So so it will be like the output would be like this. So return output, this would be a combination of all these three things, right? So it has the input, the weight, and the biases. So now we're going to do the backward. So in the backward, it will have this CTX, this output, which we took from the forward, which is here, and it will do self, because it has to do some automatic thing, and the output gradient. What is that output gradient? That output gradient is from the output of the forward. So it will take that, so performs the backward pass and computes gradients for weight and biases, because we just added the weight and biases here. So now for this, x is CTX, because for the forward x was x because it was an input, but is it gave this CTX as an output. So now for the backward, it is x is the input, which is the output of the forward pass CTX, right? So compute gradients for weights and biases. So what we have to do is we have to compute that gradient for weights and biases. Did we do that before? Yes, we did it. Look at here. But why we are doing it? Because we did it before doing the forward right here, and now we are doing it for the backward. And you will be doing the zero gradients and SGD and all everything, right? So compute the gradient for the input. For input of what? For the back pass. Input gradient np dot output gradient self weights and t, return input gradients, right? So the tensor, if keep it is can keep dims equals to true. I think I missed this. Compute gradients for weights and biases. I missed this one. So self weights equals to numpy np dot x t output gradient. So this t is eventually, that would be, I will show you how it comes up to. So it will see like keep dims equals to true. Keep doing it if it is true, or if it is true, keep doing it. Self defined biases, right, and self defined weights equals to np dot, and see the difference. The weight is the dot x t output gradient, but the biases is the np sum of the output gradients. X is 0 and keep dims to t. So this is enough for today. I'm also tired, so I'm gonna make another video by tomorrow or some other time. So I just show you, it's a lot of work here that I completed. So I will define the back prop again. So this is a backward self. See, most of the work is, I think it's rewritten. See, I was talking about the ReLU layer is here. This is like for the linear computation, and then we have all other calculations here. This is what we just defined. Zero gradients, we did it. SGD steps, we did it here. Forward and backward, I think most of the things are repeated here. So let's leave it for tomorrow, and next video I'm going to share with you. Thanks for watching and being patient. Thank you.